Hello, we are continuing with logic design concepts, and in this next part, we'll be doing storage elements. Storage elements are components that do remember something, and we will show the basic components, and then later on we will show how these basic elements, basic memory elements, are used for designing circuits that think, circuits that make decisions. I'll start with the basic latch, the very basic component that remembers something. Then we add timing to it, call it D-latch or clock D-latch. Then we make some corrections to it. We make it, we turn it into a flip-flop. Then we talk about flip-flop controls and so on. And then at the very end, we talk about registers. So let's start with this. I'm putting together two NOR gates, and look on the left. What you are seeing is one NOR gate having a feedback through the input of the other NOR gate, and actually this feedback is what causes the memory in this component. Why do I say that? Well, you can very clearly see here that the decision made on the output, let's say if this is the output, or even this is the output, the value that comes on the output of the circuit is a function not only of this and this input here, but then it is also a function of the previous outputs coming to the circuit from by a feedback. Okay, so we are saying that the output not only depends on the input, the output depends also on the previous output, and also maybe on the previous output, the one before, and the one before. And therefore what we say is that the output of a sequential circuit at time t is a function of the let's say this is the output, a function of the input at time t, as well as the output at time t minus 1, t minus 2, and so on. So instead of saying all of this, we say that, well, the output of a circuit is a function of its input as well as the present state of the circuit. Okay, and then we say that the state of the circuit at time t is another function of the present input and the previous output, previous state of the circuit, okay, at t minus 1. So really what we are saying is what you get on this output is not only, or either one of these outputs is not only a function of the present input, but also what has happened to the circuit in the past. How much does the circuit remember about its past? Well, it depends on the number of lines of the feedback. The more feedbacks it has, the more it remembers from the past. The fewer feedbacks, like in my circuit, I only have one feedback. It only remembers one thing from the past, either a 0 or a 1, okay, or maybe two things. But there is one line, since everything is binary, so the two things, it remembers either a 0 here or a 1 here. So that's the basic element and the basic concept behind memory elements. And what we have here is I've redrawn this same circuit to turn it into what is usually referred to as cross-coupled NOR gates. And even though this may look like it has two feedback, but there is only one feedback, just if you pull this lower gate forward, the right hand side circuit is absolutely no different than the left hand side circuit. So I'm claiming that this is a memory element, and I'm going to exercise this. I'm going to prove to you that this indeed is a memory element. Let's take this circuit. I'm going to repeat it here. Okay, the upper input is S, the lower input is R, the output is W and Y. And if I put 0, 0 here and just propagate the value 0, 0, Y becomes a 1 and W becomes a 0. Later on, I change my S from 0 to 1. I change my S from 0 to 1. Okay, keep this 0, and then the 1 here propagates to this NOR gate here. Okay, the 1 on S propagates here and turns my Y to 0. Y becomes a 0, and then W becomes a 1. Okay, so this is what I'm showing over here in this waveform here. See, after S changes from 0 to 1, Y goes from 1 to 0, and then as a result later on W becomes 1. Continuing on, I'm going to change my S now back to 0, keeping this as 0, and then you will propagate that. You will find that this stays as 0, and then this stays a 1. Therefore, what I'm saying is when this changes to 0, well, this stays as 0, this stays at 1. Later on, I'm going to make some changes to R and not to S, and again play with this to see what happens then. So let's put a 1 on R and keep my S at 0. A 1 on R, all right, and keep my S at 0. And let's propagate and see what happens now. A 1 on R goes over here, goes into upper gate, and because this is a NOR gate, the output becomes 0. So the output becomes 0. As a result, the 0 propagates back here and changes my Y to 1. The 1 on Y goes back here and stable, and it finds that W is stable and it stays at 0. And therefore, this is what I end up with. Maybe I should have drawn this a little bit. Let me make a little bit of correction here, because W changes first, and then as a result, Y changes. Okay, so it's probably... So Y changes to 1, and later I'm gonna make some more changes again, and this time I'm gonna change R to 0, keep S as 0, and so R changes to 0, S at 0. I find that the 0 on R propagates to the upper gate, and that remains at 0, that remains as 1, that remains as 0, that remains as 1. So that's what with these changes, starting from the same values on SR at 0, 0, and on the output the W0 and Y1, I after some changes came back to the same situation, 0, 0, 0 here. Now let's look at this circuit here. Let's say that my real output is the W output. Let's not look at the Y output. I see that at the beginning, where I'm calling at the state A, my input is 0, my S input is 0, my R input is 0, my W output is 0. Okay, so here is the situation right here. Then later on, my input is 0, my other input is 0, but my output is 1. So what am I seeing here? I'm saying that for the same values on inputs, my output is 0 at one point and it's 1 at some other time. What it means is that the output is not only dependent on my inputs, also it depends on something else. What is that something else? If I look in this waveform for this very simple circuit, I find that my output is also a function of this y variable, which is actually the feedback that comes back to my circuit. I've shown that since for the same input values my output is sometimes 0 and sometimes 1, my circuit actually remembers something. Okay, and what does it remember? Well, let's see what it remembers. My circuit remembers the following. It sees that, for example, if a 1 happens on S, my output is a 1. Or if a pulse happen on S, my output is a 1. If a pulse happen on R, my output is a 0. Okay? And therefore, I'm calling this an SR latch. S sets my output to a 1. R resets my output to a 0. Okay? My circuit remembers whether the last pulse was on S or it was on R. Okay? And that's all my circuit remembers. My circuit doesn't like to see simultaneous S and R values of 1, and therefore I will always avoid that. Alright, so this is a good thing. I have already built a circuit, this circuit over here, that I've already built a circuit that can remember something. Okay? But then the problem with this is that when I like to remember something, I have to have some timing component. Meaning that, for example, I remember from an hour ago that the values of S and R were such and such. Okay, or I remember from an hour ago that the S input had a pulse on it. This circuit I showed you here doesn't have that timing component. In order to add that timing component, I'm going to add these two gates to my cross-coupled structure. Okay, these two gates have another extra input. I call it the clock input. The clock input is a time component. It says, well, the S and R behave as they're supposed to behave, which is like this or like this. Okay? But then there is a clock with two AND gates here. It says that I will only allow external values of S and R to arrive at the internal values of S and R. Okay? These are the internals. These are the externals. Okay? For now, don't look at the structure on the left hand side. So it's saying that I only allow capital S and capital R to reach lowercase s and r only when there is a pulse on the clock. And therefore, I'm controlling the timing of this circuit. The timing of the circuit is controlled by pulses on the clock. Okay? When clock is 1, only then I will allow S and R capital to propagate into my structure and make changes to my memory. Alright, so this is the memory part. This is the timing part, the clocking part. And then what is this? What is the one on the back, on the left? On the left, what I like to remember from when I want to remember something, I like to remember a certain value being a 1 or being a 0. Okay? I don't really relate to S and R's in everyday life as much. you relate more to a data being saved. A data at some point of time is remembered, and you can count on it until you override it. Okay? The S and R are fine because they build the basic of my memory element, but then in order to make this structure remember some actual data, even a 1-bit data, I like to look at it differently. I'm going to put the data input here on the left, take that into S, and take the complement of it into R. Remember, a few minutes ago I said that the structure here doesn't like simultaneous ones on S and R. On this one, when D is 0, there is a 1 on R. At the time of the clock, a 1 on R resets this. That means at the time of the clock, the output becomes a 0. On the other hand, if I have a 1 here, I have a 1 on S, okay, and then guaranteed a 0 on R. And then at the time of the clock, the 1 on S will propagate over here, make this 1. What it means is this structure, the way it works is it takes the value of D at the time of the clock, stores it into my Q output. And then the Q output is, with this feedback here, generates the Q bar output because Y and W in the previous one were always complement of each other anyway. So instead of looking at one as feedback and one as the output, I can look at them both as two outputs which are complement of each other. That's a separate different issue, but anyway. But then the component I have here is called a D-latch. It is a clocked D-latch, meaning that at the time of the clock, it holds the value of D in the output until later on that I give it another clock pulse, okay, and then it's overwritten by new data. So that's a good memory element. It's called a D-latch. It's called a clocked D-latch. Well, what's one bit of information? I mean, when we say we need to remember something, we need to remember lots of things. But then what's one bit of information? Well, that's okay. You can, instead of having one of these, you can have 4 of these. You can have 20 of these. You can have 32 of these. And then remember 32 bits of data, or remember a 32-bit data. Okay? And therefore, in order to have more data saved or bigger data saved, I'm going to put these into a I'm going to take 4 of these, put them in parallel, and each one of these is one of the D-latches I showed before. Okay, is one of these, and now I'm saving 4 information. At the time of the clock, notice that there is one single clock that when it becomes 1, it takes the I inputs and stores them in the W outputs. Okay, this is, by the way, is also called a register. Actually, a register is only the definition of the register is simple. When you have, instead of one latch, if you put 20 latches with the same control, with the same clock, that becomes a 20-bit register. This is a 40-bit register made of latches, or you can also call this quad latch structure. And instead of drawing all the details inside the latch, I'm going to reuse this representation. This representation says that at the time of the clock, C1, look at this one over here. Okay, look at this one over here. At the time of the clock, when C is 1, then the D input is accepted. And the way we look at that is the following. We say that this line, if there is a 1 on the right hand side, that's a controlling signal. If there is a 1 on the left hand side, that's a controlled signal. That means the clock controls the D input. That means when the clock is 1, the D input is accepted, and when the clock is 0, the D input is not accepted. This is exactly what we are showing in this logic over here. When the clock is 1, the D input is accepted by these AND gates. If the clock is 0, the D input is kind of stopped. Alright, so that's a quad latch, and this is a symbol for the this is a symbol for the latch itself. The problem with the latch is that it is transparent. What does it mean, transparent? Well, look at this over here. When the clock is 1, okay, the AND gates open. Okay, when the clock is 1, meaning during this time here, the AND gates are open. The AND gates are open, that means the D propagates through here, also through here. Okay, and then there's nothing to stop it from here. Okay, and this. What it means is when clock is 1, a 1 on input D propagates all the way through to the output. If it changes to 0 while the clock is 1, then if it changes to 0 while the clock is 1, the 0 also propagates to the output. That means it's transparent. During the time that the clock is 1, it is transparent. It lets the input values propagate through. If you don't like that, okay, or why wouldn't we like that? Well, see, the problem with what I just did is, if ever I have some combinational logic and this output goes into this combinational logic, okay, let's say a series of AND gates and OR gates, if I ever take this output and bring it back to the input of this latch, during the time that the clock is 1, I will have a combinational loop. I will have a situation that my circuit will be oscillating. Let's, for example, say that this combinational circuit on the upper right hand side is a let me redraw it here. Let's say this combinational circuit is just an inverter. And this inverter is fed back into this. Okay? During the time that the clock is 1, this latch is transparent. That means if the input is 0, the output becomes a 0. If the input D is 1, the output becomes a 1. Now this 1 and 0 goes into this inverter and gets complemented. During the time that the clock is 1, the complement goes back here and then comes back here through the output of the D latch, and then it oscillates back and forth again. So for as long as my clock is 1, this will be oscillating. Alright? In most of my sequential circuits, I like to have feedbacks. I like to have a feedback that can take the old values and use them as new values for the next clock. This situation is not going to allow that. Okay? Therefore, what I come up with is flip-flops. Flip-flops are not transparent. Actually, flip-flops are like two gates that one is open at one time and then the other one is open at some other time. For example, the way it works is when there is a 1 on D, on the rising edge of the clock, this one it says on the rising edge of the clock, the D input propagates to the output and makes the Q output 1. But as soon as the output becomes a 1 and the rising edge of the clock is passed, the output remains a 1. And if you have a feedback through the input, that feedback will not happen until the next clock edge. This is called, the one on the left is called an edge trigger D flip-flop. The one on the right is also an edge trigger D flip-flop. The one on the left is a rising edge D flip-flop. The one on the right is a falling edge D flip-flop. Okay, what it means is the one on the left, the input is taken. The input is taken when the clock makes a transition from 0 to 1. The one on the right, the input is taken when the clock makes a transition from 1 to 0. With this edge behavior, the input is only taken on the edge. That means when the input propagates to the output, the edge of the clock is gone, and therefore the even if you have a feedback, the feedback will not happen until the next edge of the clock. And actually, this is what I talked about already with the flip-flops. This situation can it doesn't cause a problem. If I have latches here, with the feedback, this is going to create unpredictable results because I really don't know how long the clock is on and how much propagation because of the delays and all this is going to happen. With the flip-flop, I'm pretty sure that the combinational logic will only pass through one clock and then the feedback will not happen until the next clock. Alright, so what we have done is we have talked about latches. Okay, and this is a latch symbol. We have talked about flip-flops. This is a flip-flop symbol. Still, I'm showing that the D input depends on the rising edge of the clock. Okay, and this is a latch. This is a flip-flop. Okay, a flip-flop stores something and is not transparent. The latch stores something, but it is transparent. How do I build latches? How do I build flip-flops? Well, let's look at this example here. In the stores, when you have, or in the offices, when you have cold air inside, hot air outside, if you open the door, what happens is it becomes transparent and the good air-conditioned air will flow out. The hot summer, well, it's winter here now, but the hot summer air will come inside. To avoid this, what they do is they have two doors. Okay, and the way it works is one door opens and the person comes here, and then the door closes. This other door opens, and then the person comes inside. Okay, soon as the person comes inside, this door closes, this door opens again, and therefore there will be no time that there will be no time that you have a transparency of airflow between the outside and the inside. And the concept of flip-flop is exactly the same way. Instead of having one flip-flop, one latch, you have two latches. The two latches work opposite to each other. There is a clock input. Look at the diagram above. There is a clock input that opens this latch on the left. This latch on the left is like this door. Okay. When this opens, the data input goes halfway in the middle. When the clock is 1, but then when the clock is 1, this one is 0, and therefore this latch, which corresponds to this door, is closed. As soon as my clock becomes 0, this latch closes, okay? And then the person here propagates from here to here, shows up over here. Okay? So, this is what happens. This is my person, the input, and when clock becomes 1, the D input goes halfway. When clock becomes 0, the D input goes the other half and appears on the output when the clock becomes 0. So this is in a way equivalent to a behavior-wise is equivalent to a flip-flop with falling edge clock. That means the output only changes on the negative edge of the clock, but then this flip-flop never has transparency. This, by the way, is called a master-slave flip-flop. Okay, which is different than the edge trigger, but conceptual or principally both work the same way, and they both do not have the transparency. All right, so this is this is, by the way, again is master slave flip flop.